We live in a universe where h bar, the fundamental constant that sets the scale at which quantum effects become noticeable, is very small compared to everyday scales. But imagine a world where Planck's constant is much bigger. How would this change our perception of even everyday macroscopic objects? Let's consider the following problem. Fuzzy the duck lives in a world in which h equals 2 pi joule seconds. Fuzzy has a mass of 2 kilograms and is initially known to be within a pond 1 meter wide. What is the minimum uncertainty in his speed? Assuming this uncertainty in speed to prevail for 5 seconds, determine the uncertainty in position after this time. In the uncertainty principle for a baseball, we discussed how an uncertainty in the measurement of an object's position leads to a lower bound on the simultaneous measurement, and the uncertainty in the simultaneous measurement of the object's velocity from the uncertainty principle. So we discussed how delta V is greater than or equal to h bar over 2m delta x. Here, we know that the initial uncertainty in Fuzzy's position is 1 meter because we know he starts out in a pond that's 1 meter big. We don't know where he is in the pond. So, of course, the interesting thing in this problem is that we want to know what this uncertainty in his velocity is. For a macroscopic animal of mass 2 kilograms, in a world where h equals 2 pi joule seconds. So since h bar equals h over 2 pi, this means h bar equals 1 joule second, which is 34 orders of magnitude bigger than the value of h bar in our world, and in particular is on the order of the mass of the duck. So plugging in to this inequality, we would find that initially our uncertainty in Fuzzy's velocity has a lower bound of 0.25 meters per second. So the question says that this uncertainty in his speed is to prevail for 5 seconds. So what does this mean? That means initially the best we can tell what Fuzzy's speed is only up to this uncertainty. So if Fuzzy does have the top speed in this range, then he could move a distance in that 5 seconds of what we'll call delta x prime of at least delta v delta t, where this is the 5 seconds and this is the 0.25 meters per second. So plugging in the numbers here, in those 5 seconds, Fuzzy could have moved at least 1.25 meters. Because initially, we didn't know his velocity precisely, only up to an uncertainty of 0.25 meters per second. So what does this mean? This means that our ability to measure Fuzzy's position has actually gotten worse. Initially, we only knew his position with an uncertainty of 1 meter, and then we only knew his subsequent position with an uncertainty of 1.25 meters. So the net minimum uncertainty in Fuzzy's position after 5 seconds has grown. So I'll call this the minimum uncertainty after 5 seconds is the initial uncertainty plus this uncertainty in the subsequent 5 seconds. And plugging in the numbers, we would find this equals 2.25 meters. After just 5 seconds, Fuzzy could even be out of the pond. After just 5 seconds, the minimum uncertainty with which we know Fuzzy's position is 2.25 meters, more than twice the width of the pond. So Fuzzy may be in the pond still, but he may not be. We have no idea. And Fuzzy is a macroscopic animal. So Fuzzy is an appropriate name for our duck. Because of the uncertainty principle, he doesn't have well-defined boundaries. He actually would appear fuzzy. Okay, so now of course, even in this strange world where h bar is so large, this delta v still goes like 1 over the mass. The important ratio here is h bar over the mass times delta x. So a more massive animal than Fuzzy, say an elephant, a more massive animal than Fuzzy would have a smaller uncertainty in their velocity, and therefore would end up with less spread in the uncertainty of their subsequent position. So an elephant in this world would still appear more well-defined than Fuzzy or a duck because an elephant is bigger. So this reiterates the point that quantum effects are more noticeable for smaller objects, even in a world where h bar is so big that a duck appears fuzzy.